So let's get some practice applying this strategy for finding the surface area of a parametrized surface. And again, the way that we want to do it is by parametrizing the surface, so getting a parametrization, deciding what range of parameters s and t describe that portion of the surface that I'm interested in finding the area of, and then evaluating the magnitude of the cross product of the partial derivatives of my parameterization. That becomes my integrand. I know what ranges of parameters that define my region in ST space that we want to do the integral of, and so we just have to do that double integral using that magnitude of the cross product as the integrand. It's, by the way, very often the case that these integrals get hairy, like to do from an analytic perspective, because taking the magnitude of something that has variables in it, right, is going to necessitate the square root of a big sum of squares of things. And any function which is defined as the square root of a sum of squares of like variable expressions, antiderivatives are very hard to come by in the general case, in an analytic sense. And so the bad news is that this is not most of the time in the real world, right? If somebody comes up to you on the street and hands you a surface area integral, it's virtually going to be impossible to do with analytic methods. And so if you're ever having to do this on the job as a mathematician, applied mathematician, a physicist, an engineer, a lot of times you end up doing numerical approximations to integrals like this one. For the sake of our course, we're going to kind of create a little safe space where all of the surface area integrals that we do end up being doable, but there just aren't that many of them that are out there. And so it's, I think, one of the hardest jobs in all of professional mathematics is being the author of a calculus textbook that has to write a section of problems and exercises on surface area and arc length and curvature. These are like all of those integrals, all those quantities involve, integrals of square roots of things, which are almost always impossible to find analytic antiderivatives for. So that's just a word of caution about this. But in this problem, it'll turn out to be quite nice. So we don't need to fear because, again, we've created a safe space in this activity. So we want to find what is the surface area of this portion of a cylinder. So it's a cylinder of radius a, and so a is constant here. And its height is h, so it goes from the height z equals 0 up to z equals h. And so we have a parameterization, we have a range for our parameters. Now, we could find the surface area of this cylinder using ordinary geometry. This is one of these classic kind of problems where, oh, it's the label on a soup can. How would I find out the area of the label on a soup can? I'd probably just cut this cylinder and lay it flat on a table and just find what's the length and width of that rectangular soup can label, and that would be the same as the surface area of this cylinder. So again, this is one of these great calculus problems where we already know what the answer is going to turn out to be. And so it's more about getting the practice of setting up the surface area integral that could yield us that answer, which is then more flexible to use in other cases where geometry doesn't give away the spoiler. So we'll set up an iterated integral to determine this surface area using the parameterization, and the parameterization is handed to us here, so we don't even have to do that work. Evaluate that iterated integral, and then if we want to do part C, probably we won't, we'll think about a different way of finding the surface area that we could have done in single variable calculus by just slicing this cylinder horizontally and integrating the perimeters of those circles, the circumferences of those circles, from 0 to h. But parts A and B here are where the real interest is in this problem. So let's tackle those two parts to get us started. So this example turned it out to be not so bad, right? This parametrized surface, when we find the magnitude of the cross product of its parameterization, that magnitude of the cross product ends up being the square root of a squared times cosine squared s plus sine squared s. And cosine squared s plus sine squared s gives us 1, and so the magnitude of this cross product just ends up being a. So every one of the little normal vectors to our surface that comes out of this parameterization by taking the cross product of the two partial derivatives, every one of those normal vectors has the same length. They're all equal to a. And so when I do this integral, it just ends up being the double integral of the constant function a, from s ranging from 0 to 2 pi, t ranging from 0 to h. And when you evaluate that, it's nothing more than a times the area of the rectangle in ST space, which is 2 pi wide and h high. All right, so 2 pi h times a gives us the surface area right? And 2 pi AH is how we would have computed the surface area of this cylinder if we had treated it like a soup can label and just cut it, right? It's the same as the circumference of the circle, 2 pi A, multiplied by the height, which is h. So classic example of calculus telling us something that we might have already expected from geometry, but this is in a way where those sort of formulas from geometry that you might learn in high school, it's where those kinds of formulas come from. And so real quickly, what I want to do next is just kind of talk about how we might come up with a formula for the surface area of a sphere in the process as well.